Hello children, welcome back to physics. Ready, set, do this question. Great job. Two conceptual things. When the rock comes back down to the same height, it'll have the same speed, but reversed. And the acceleration is always 9.8 meters per second squared downward. And at the highest point, the speed is 0. These are all just like kind of like checklist of facts that we use a lot last few units, but time for a new topic. So, what am I talking about? You guys probably know that Google and Apple and many companies are like super oligopolies and control all your data. Oh, Facebook too. And they pretty much know where you are your whole life. People say, oh, I don't want to get a coronavirus vaccine because they're going to use 5G cell towers to track where you are. You already have smartphones that are doing it for you, so not necessary. In fact, if you downloaded your data, you could figure out where you were and when you were at these places. Pretty much your whole life, as long as you've had a phone. The government and the NSA could track your whole life if they wanted to, anytime. They could record this information if they wanted to. That would not be that hard. Before we get into that, I gotta talk to you guys, remind you guys about displacement. Displacement is just a very fancy physics term for how far you've come and in what direction you've gone from your starting point. If x is position, then x naught, or x subscript 0, is your initial position. And the displacement d, which we use a lot, sorry for the glare, is just d equals x minus x naught. So on the equation sheet, you get like all these big equations with x's and x naughts on either side, and it's kind of like a lot of letters. To make it simpler, I always, in my head, substitute d for x minus x naught, displacement of x minus x naught. We're going to do that today, as usual, but we're going to keep it really even simpler. We're going to say x naught, we'll call that position 0, 0 meters. Let's say you start at 0 meters, you're on a number line, you can go forward into the positive x direction or backward into negative x. So if you're at 5 meters, you're 5 meters forward of x equals 0. 0 meters, the starting position. So if x naught is 0, I might have confused you guys, but real simple. If x naught is 0, d equals x. They're basically the same thing. So let's say we have that. Let's say we happen to know, let's say we are the FBI and we know where you are your whole life. Let's say we know that you started out at 0 meters. Then let's say we know that 3 seconds later you were 9 meters ahead of your starting point. And, I don't know, 6 seconds later you were 18 meters ahead of your starting point. It's pretty obvious to you guys, but how can we find our velocity? How do we find the velocity? If I know that I started at some location, and then 3 seconds later, I was 9 meters ahead, and 6 seconds later, I was 18 meters ahead. This is a very obvious, simple case. But in general, to find out my speed at various times, I'm going to use a graph of displacement versus time. So we're going to look at graphs all day, today and tomorrow. For these graphs in physics, the x-axis is always time. The y-axis will change. For now, it's displacement versus time. So you plot the data. I got nice, neat data on purpose. So there we go. 9 meters, 18 meters, 3 seconds, 6 seconds. Oh, a nice straight line. Perfect. I know you guys all know the speed is 3 meters per second, the velocity is 3 meters per second forward, but we're going to look at it more in depth. How do we know that's true? Look at this graph. We know displacement and time. We have lots and lots of data. And the data could be crazy. We'll see a graph diffusing this looks like just very crazy. Let's say we're trying to find the velocity. Well, we all know the formula for velocity. V is displacement over time. It's technically average velocity, but if you want to instantaneous velocity, it would be the same thing, just for very small displacement over a very small time. I wrote them small because they're small. That makes sense. Duh. So we want to find displacement over time. Well, look at this graph. Displacement is y, and time is x. Oh my gosh, we're about to have a big brain moment. Delta y is the displacement. Really, it's change of position. But if we consider that the initial position is 0, then delta d is delta x. I shouldn't use x, obviously, because x is the time axis. So that's why I switched to displacement. Delta x on this graph is the change in time. Oh my gosh. What's another word for delta y over delta x? Do you know? Hazel? What is it? What's delta y over delta x? You guys tell me right now. Good job, everyone. Delta y over delta x is the slope of the graph. And this is always true. The slope of a graph, it has to be d on the y-axis and time on the x-axis. The slope of that graph is velocity. So I'll write it down. The slope of d versus t, it's velocity. Technically, it's the magnitude of the, no, it's not the magnitude. Technically, it's velocity. You can only have direction, but you can have sign. A positive slope would be a positive velocity. If the slope were somehow negative, pointing down, that would be a negative velocity. So I'll just draw a quick second example. Let's say I'm the NSA and I'm tracking, some sort of weird criminal, and I can see, oh, they went over here, then over here, then over here. I would say, they left their house, and look, this is a very high slope. They're moving really fast. But then, what happens to the slope around 3 seconds? The slope goes 0. This is 0 slope. That means 0 velocity. That means they stop moving. Then what happens? Oh, well, then we have a negative slope. That means they were going backwards. And I could be a great FBI agent and track someone's whole life and determine exactly where they were at every point in time and decide whether or not they're like a major threat to national security if I felt like it. That's the idea. The slope of d versus t is velocity. Okay. That's fine. But we know about another important quantity in physics besides velocity, obviously. We also know about acceleration. If you know calculus, you might be able to figure out acceleration, but it's not quite that easy for most students. So this is really useful because in this simple example, displacement versus time, we could find, let me make a new example. I have to do some quick mental math, but I'm a genius, so it should be no problem. Let's say for every time I know my displacement, and I want to find my velocity. Okay, this is fine. The time, that's a t, it's covered up by the glare. Time in seconds, displacement in meters, velocity in meters per second. Okay. let's say 0, 1, 2, 3 seconds, and I was at 0 meters, but then 1 second later, I was 2 meters away. And then 2 seconds later, I was 8 meters away. And then 3 seconds later, I was 18 meters away. And that's my math skills. Perfect numbers that work out perfectly because of reasons. So I can make a nice graph of d versus t, and it would look like this. I happen to know it would look like this. I didn't actually graph it, but trust me, because I said so. All right. So the nice thing about this, you can't tell your speed at every single second from this data. It's not easy numbers like the last one where it was clearly just 3 meters per second all the time. But you could figure out the velocity by measuring the slope. So I'm going to do that. Delta y over delta x, delta y over delta x, delta y over delta x. Good job, me. I did it. I discovered by measuring those delta y's, delta x's, even though you couldn't tell because I did so fast, that the velocities were 0 meters per second, 2 meters per second, 4 meters per second, and 6 meters per second. I happen to be an excellent super light speed measurer and divider to find those velocities. I did a great job. So let's make a graph, not of displacement versus time. Since I know the velocity at every single time, I can make not a graph of displacement versus time. I want to make another graph, velocity versus time. And amazingly, oh my gosh, it ended up being another straight line. But this is not, this is a curve, this is a line. How do we find acceleration? I know this formula for acceleration is delta v over t, but really it's basically kind of the same as delta v over delta t. Look at the graph. What about this graph could be an acceleration? Tell him, Daisy. The slope. Wow, good job. Oh my gosh, what a scholar. Yes. Pick any 2 points. Delta y is delta v, because the y-axis is the velocity axis. Delta x is delta t, because the x-axis is the time axis. It's the slope. Again, don't be confused. We just said that v is the slope for d versus t. A is the slope for v versus t. But only of a v versus t graph. So we're going to end a little early because it's pretty quick but pretty important. Let's see how big your brains are. We know that for a d versus t graph, the slope is the velocity. We know for a v versus t graph, the slope is the acceleration. We would never really talk about the slope of an a versus t graph. But here's a big brain question. How could you find acceleration from a d versus t graph? It's a pretty tough question. Right? Right, Sage? Yeah, I have no idea how to do it. Well, if velocity is the slope of d versus t, do you have any ideas? You can tell me if you do. Okay. If velocity is the slope of d versus t, and acceleration is the slope of v versus t, you could look at the slope of the slope. What does that mean? I'm in pre-calc. I'll tell you. The slope is how fast d versus t is changing. But if you look at how fast the slope is changing, well, the slope is v versus t. So that would be how fast v versus t is changing, which is acceleration. So if you have a graph of d versus t, it's definitely hard to tell, especially if this is your first time hearing about it. But if you see the slope, like let's say I had a d versus t graph. Can you guys see this? It's too low. Just kidding. let's say I had a d-verse graph that looked like this. Wow, this is a very large negative slope. This is a very large positive slope. Here, right here, the slope went from this to this. The slope changed a lot, and the slope is velocity. So the velocity changed a lot. That means there was a lot of acceleration. So if you have a d-verse t graph, the slope is velocity. If you want to be big brain, acceleration is how fast the slope changes. Or you can just make a graph of velocity over time, then just the slope is acceleration. Thanks for listening to my great lesson.